is you can now get even more than 40% improvement. Sorry. And yes, it's only 25% to compare to an optimized shared channel. The difference is just in the one point you use the old legacy channel, you're about here, to the optimal point of there, and in the other value you compare this value with that value. Unfortunately, this improvement, the more than 40%, which is quite impressive, won't be usable if you have two TCP connections flowing in opposite directions. There you will again find this degeneration of throughput. This again happens because there are TCP data segments, rather large packets, and TCP acknowledgement segments, and they interfere with each other. So it's quite the same like on a shared channel, that they both stick in a queue and the acknowledgement get delayed, and TCP is very high. The result will be really high affected by delaying the acknowledgements. You can even simulate this just by using Linux NetFilter and tagging TCP acknowledgement packets and delaying them with the network emulation principle to a random number, and then you will see that the throughput of TCP will decrease dramatically. Okay, but if you look in literature, you find some interesting papers on how to solve this problem, which is called the TCP ACK congestion. The first one is just, as you might perhaps remember, the TCP acknowledgements acknowledge the latest packet they have received. And if you look in intermediate queues, there might be more than one acknowledgement for one TCP session. And so at least one packet will be redundant, and the queue can remove this acknowledgement. It's quite a strange concept, but it seemed to work, at least in the papers I've read. Another concept will be the ACK prioritization I implemented in this method. It's just, again, using TCP NetFilter, taking the TCP acknowledgement segment and put it in the higher priority queue. As you see at the 800.11e standard, you have 4 priority queues. Now you don't use it for voice, video, background, and best effort differentiation. You now use them for normal flows and high priority flows. And the high priority are the TCP acknowledgement segments. It was a bit difficult to implement this, at least on the slow Sucrus PCs, because they ran out of software interrupts and slowed down dramatically. But at least another test with a bit stronger PC showed 5.2% increase in throughput. This might be also too small number, and should be again tested with a really high-speed PC or 2 high-speed PCs with Wi-Fi connection, because it's at the moment not the best implementation to do this. There's a really cool way to do this. It's called ACK congestion control, where you don't acknowledge every data segment, or nearly every data segment in a TCP window, but you can control when acknowledgement for TCP frames can be sent, and when you experience there might be congestion in the network, you decrease the number of acknowledgements you will send. This will have a bit an impact on throughput increase and decrease of TCP, but it will at least not suffer so much from the situation found on the Wi-Fi link. And now, shortly, the conclusion. Okay, you can, as I showed you, you can use 802.11e parameters on a shared Wi-Fi link, and you can increase the throughput significantly. It can be up to 30% for UDP. So it would be nice to have it on a point-to-point link. And the other solution, if you also want more throughput for your TCP flows, and the most packets in the internet are TCP, you can use the other idea and increase at least 40 or 26% for your TCP flows. And if you have a situation when there are a lot of traffic in one direction and in another direction, you can use this actorization. Perhaps you will implement it a bit better than I did and get more than these 5.2%. If it's so, write me an email. And okay, this for that. But the main idea behind this, as I showed you, it's possible to do some optimizations and you get a real significant increase in throughput. But you will have to use a second channel. This is perhaps really expensive. And so there is the main idea behind this, to use this within a mesh network. But not within a mesh network like the Freifunk.net people using the same channel for every link between the nodes, but in a multi-radio, multi-channel mesh network, so that you can easily implement this, even if this leads to a bit a strange and asymmetric routing, using on the forward direction perhaps 1 or 2 hops, and on the backward connection you might use 5 hops and so on. In the normal internet, every scientific paper will say this is a really stupid idea. You should use the same path in the internet for forward and backward direction. Okay, it's not the reality in the internet, and in the wired internet perhaps it's also not really interesting. But at least they will tell you this. But remember the OLSR in later, I think for some years, 2 or 3 years, they also used hop count as a primary routing key for building a path from one node to another, but they soon realized this is not really a good metric for your routing. Perhaps it's better to use the expected transmission time between 2 hops, between 2 nodes, and not really the hop count. So the main problem will to be in the future to find good pairs of different paths between 2 mesh network nodes who have an equal transmission time, or an expected equal transmission time, and there to use this idea to separate forward and backward direction to get this improvement without the high costs, as I was showing in this test bed. Okay, I already implemented some parts of this, but it's not really quite stable or working yet. It's primarily intended to use OLSR and to do some extensions to have 2 pairs for 2 paths, or a pair of 2 paths with equal time. Perhaps we will see in the summer at the camp more details on this, and if it's really working or it was really a stupid idea, we will see. So thanks for listening, and we have only 5 minutes for questions.
Thank you for your talk. I asked me if there are, why are these parameters fixed? For example, I would try to add an adaptive strategy that, depending on the traffic that both sides see, either symmetrical or asymmetrical or UDP or TCP, I would adapt the parameters to the optimal solution. So you could even change the protocols. I'm not a Wi-Fi expert, but you could do a lot of optimizations on the fly if you have an adaptation strategy.
Yes, you're right, you can do this, but at the moment I didn't implement this because I need some sort of information transport. Because normally when you have point-to-point link, you need the measurements of the other side also to give good decisions or strategies for the traffic. So you need communications between both sides. And how often do you communicate? This is also the next optimization problem. You cannot just for every packet you send another packet indicating I have sent a packet. So what's a cool way to do this communication, and how often you will do this? At the moment I don't know, but you're right, this would be another cool idea to do on-the-fly optimizations. But we will see. Not at the moment. Any questions left? Oh, okay, one.
Hello. What hardware and Linux driver do you use for the experiment on your experiment on double WLAN experiments? What hardware and Linux driver do you use for 802.11e?
And you want to know which Linux drivers I use, or
yes, or which
Wi-Fi?
Yeah.
I normally use Atheros cards. The newer ones which support 800.11a, and the normal MetWiFi driver, the normal HAL driver, not the open HAL driver, and yes, okay, the latest stable version. Not there are several branches in the subversion, but I normally use a normal branch.
Okay, thank you.
Okay, if there are no questions left, I would like to say thank you to Achim Friedland and thank you for listening.